Practical machine learning for computer vision. In this session today, we'll be looking at the training loss. Training loss is also referred to as the cost function or the objective function, and essentially the optimizer tries to minimize the training loss, or what you call the training error or model error on the data side. So it chooses weight that achieves that minimization. And so there's for classification problem, you can choose a cross entropy loss as the error to minimize. And the formula for the cross entropy loss is shown in here. So here the L high, the LJ is the true class, while the PJ is the probability that the model gives us. So you sum up all those, you take the log of the probability, you multiply that with the true class, and you sum up over all the classes. That's essentially how you calculate the training loss. So for every forward propagation, you do that, and you do that over all the different instances in a batch. Okay, so and how does this actually work? To explain what this cross entropy loss is doing, is saying if the probability of predicting a correct label, if it is 1, so let's say that the model output a probability of 1. So if substitute 1 here, log of 1 will give us 0, and by multiply a 0 with whatever you have here, that is going to give us 0. So that means the probability is going to be the error is going to be minimized, so we're going to have a loss of 0. On the other hand, if the model gets wrong and the probability is 0, the log of 0 is going to give negative infinity, and if we multiply that by this negative, then that's going to give positive infinity, which is the worst possible loss. So that's essentially what the training loss is about. And you can either code your output as either 1/0, or you use a sparse coding. So if you use 1/0, this is how the cross entropy is defined. Okay, and if we use as integer indices, this is how it is defined as shown in here. So let's look at the two ways of representing the label, which is 1/0 encoding and the sparse encoding. So if we use a 1/0, you typically have a vector that is the length of the number of classes, and you just put a 1 wherever you have, if the class is present in that particular image. So what this 1/0 encoding helps us to do is, it helps us to do a multi-label. So if the class is present, if there are 2 classes or more present in a particular image, so you can just turn the corresponding zeros to 1. But if you're using a sparse encoding, you will not be able to achieve that. So that's the problem, because in your sparse encoding, you just put a number. So you put 0 for Daisy, and you put 4 for the other class. So let's say you have 5 classes, 0 for the first class, 1 for second, up to 4. So the downside of the 1/0 encoding is that it takes space. All right, let's start. So let's look at the error metrics. So the error metrics that you normally use is accuracy, precision, and recall. And you use accuracy when you have if the data set is fairly balanced, But if the data set is not balanced, like in this case, then you want to go for precision, which is measured by this true positive over true positive plus false positive, or recall, which has the false negative instead. Or you use the F1 score, which is the harmonic mean of the precision and recall, and it's calculated this way. And you can use the ROC curve, which varies the probability at different threshold, and you can see if you increase the sensitivity, excuse me, if you increase the cutoff at different point, you can see how the performance is. So the area under the curve gives the measurement that we require. One last thing before I leave is you see the confusion matrix here that actually talks about the actual fake, the actual genuine, and you have the identifier, that is what the model identified, the output of the model are shown on the column, while the the actual distribution in data set is shown on the row. All right, thank you very much, and see you in the next one. Bye for now.